So we continue the stack data operations of 8085. We have already discussed that there is a stack pointer, that is a 16-bit register residing inside 8085. It is always addressable as a pair and initialized using the instruction LXISP opcode is 31. So LXISP data 16, that makes stack pointer initialized with its dual stream value. There are few more instructions with stack pointer. It can be incremented or decremented manually also. By manually means by a separate instruction also, that is DCXSP and INXSP. But these are normally not supposed to be used. Stack is expected to be operated on its own by the stack operations. We also can have an instruction DAD-SP. So SP is a register pair used for stack data operations. It is available as a pair only, and some instructions like INX, DCX and DAD are applicable for that pair also, and it is initially using LXI. Then the stack is nothing but a separate area, means it is not an exclusive. It can be addressed by any other operation also, but normally it is depending upon the programmer. That this means, suppose that you have a notebook. In the notebook you write down, you spare last few pages for some purpose. Is it that for other purpose you can't write there? You can write, but you normally not write, don't write. Are you getting me? You have a notebook. In the notebook, some last page sections you write, you reserve for some specific operations that you write there. But otherwise, if you want to write, you can write anything. So it is means it is not stopped by or prohibited by some kind of restrictions, but all this care is to be taken by the programmer. You decide not to write some things in some area, and some area is to be used for some specific purpose. Like that, the external memory is used for storing data in a systematic manner by using stack. So normally we will come to know that, we will come to that also, because that also requires it. This is something which is called as interdependency. We discussed a few weeks back when you were not understanding. Hope that you are understanding now. That call instruction. Call instruction itself requires stack. The stack related operation of push is required for call operation itself. So whether first to teach call or first to teach stack operations. So it is a, what we can say, some kind of interdependence. So the register pairs are inside 8085. There are general purpose registers, accumulator, then its associated flag. So for storing purpose using stack, accumulator plus flags is acting as a 16-bit register. It is also acting as a register pair, not used for any other operations, but it is a 16-bit of this upper byte of flag register. Only 5 bits are valid. There are some position S, Z, AC, P and CY from D7 to D0. Some middle positions are vacant. So that 8-bit flag register with 5 defined flags. Are you getting me? 8-bit flag register with only 5-bit position defined and remaining undefined. The few researchers like you 40 years back have thought about some unknown undefined flag X5 like that. So 8 bits of flag register, accumulated 8 bits. This together is one register pair only used for stack data operation, that is called as program status word, PSW. Program status word, because accumulator is one of the default operands for arithmetic logic instructions, and flags are used reflecting the result of arithmetic logic instructions. So accumulator and flags together is called as a program status word. Then next register pair is obviously DC, which we know. Next is DE and next is HL. And below that we are having program counter higher byte, program counter lower byte, not accessible separately, stack pointer higher byte, stack pointer lower byte, and W and Z, which is that way hidden. means not accessible for the programmer directly, used by the processor for internal operations. Right. So using stack, we normally store these 4 register pairs on stack by the process that is pushing on a stack. When we store register contents into memory in a systematic manner, we say we are pushing on a stack, and when we retrieve it back, bringing something back or loading the register pair from memory by using stack related operations is called as pop. Push and pop. So there are 4 push instructions. Push register pair, but the register pair for this purpose is, I would like to make very clear. When register pair is there are different meanings of register pair. So for example, we are having LXI register pair data 60. So in this, which register pairs are permissible? BC, DE, HL, SP. So LXI SP instruction करता LXI register pair data 16 load immediately the register pair. त्याच्यामध्ये register pair कुठले येतात? BC, DE, HL, SP. पुन्हा दुसरे register INX आणि DCX register pair. त्यामध्ये सुद्धा ह्या येतात BC, DE, HL, SP. So for this group of instructions, register pair means BC, DE, HL, SP. There are 2 more instructions which also have register pair. What are those? There are 2 more instructions which you have studied, which include register pair. What those are? I hope. What? LHLD? No. In LHLD, you give the address directly. Then there is one more called as DAD. So for DAD also, DAD RP, again same. Means in normal case, RP means BC, DE, HL, SP. For instructions, LXI, INX, DCX and DAD. There are 2 more, somebody told. What are those? LDX and STX. But for that, what are the register pairs? BC. There are 2 more called as LDX and STX using RP. So in that case, only BC and DE. Not even HL, not SP. LDX, STX instruction also is register pair, but only 2 are defined for that. That is BC and DE. Whereas for push RP, for push register pair, BC is allowed, DE is allowed, H is allowed, but not SP, but PSW. So there are 4 push operations, 4 push instructions. Push PSW, push B, push D, push H. Is it right? There are 4 push instructions. Those are C5, D5, E5 and F5. The 4 push operations. You of course push B. You just confirm, I am not so sure about the of course. Push H and push PSW. B means BC pair. B higher byte, C lower byte. D means D pair. D higher byte, E lower byte. H means HL pair. H higher byte, L lower byte. PSW means flag higher byte, accumulator lower byte. Flag higher byte, accumulator lower byte. Flags and accumulator. So, how push instruction of? This is 1 byte instruction. Each push instruction is 1 byte instruction. I will describe how push instruction works. Push instruction is 1 byte instruction. It arranges, listen very carefully, slow speed English bulletin. Push instruction is a 1 byte instruction. It arranges to store a given register pair in the memory. So since a register pair is to be stored in the memory, how many So one byte instruction, obviously in the first machine cycle opcode will be fetched. Then since it is intending to store a register pair in the memory, how many addition cycles are needed? मराठीत सांगतो. पुश ही 1 बाईटची इन्स्ट्रक्शन आहे. पहिलं बाईट ऑपकोड फेच. पुश इन्स्ट्रक्शन मध्ये दिलेली रजिस्टर पेअर मेमरी मध्ये स्टोअर करायची आहे एका स्पेसिफिक पद्धतीने. तर स्पेसिफिक पद्धत काय हा आता महत्त्वाचा विषय नाही. काय करायचं आहे, दिलेली रजिस्टर पेअर मेमरी मध्ये स्टोअर करायची आहे. रजिस्टर पेअर म्हणजे 2 बाईट्स. एका मशीन सायकलला किती बाईट स्टोअर होऊ शकतात? 1 बाईट. त्यामुळे किती ॲडिशनल मशीन सायकल्स लागतील? 2. फर्स्ट machine cycle opcode fetch F, second machine cycle memory write, third machine cycle memory write. And what is the procedure of storing? Push instruction first decrements stack pointer by 1 and then stores the higher byte of the register pair into the memory address for which is given by the stack pointer. Then it again decrements stack pointer by 1 and stores the lower byte of the given register pair in the memory at the address given by stack pointer. Push register pair मध्ये आधी stack pointer 1 न कमी केला जातो. त्यानंतर जो stack pointer मध्ये व्हॅल्यू आहे तो ॲड्रेस वापरून दिलेल्या रजिस्टर पेअरचं हायर बाईट मेमरी मध्ये स्टोअर केलं जातं. स्टॅक पॉइंटर पुन्हा एकदा कमी केला जातो आणि मग पुन्हा एकदा कमी केलेल्या अशा स्टॅक पॉइंटर मध्ये जी व्हॅल्यू आहे ती ॲड्रेस म्हणून वापरली जाते आणि तिथं मेमरी तिथं दिलेल्या रजिस्टर पेअर मध्ये लोअर बाईट स्टोअर केलं जातं. सो विथ दिस I write 2 instructions and expect that you should be able to write the entire sequence. 0 0 0 0 LXISP 8000 0 0 0 3 LXIB 5544 0 0 0 6 आणि दोन्ही एकदम शिकूया आपण. 0009 पॉप डी. पॉप डी पॉप मध्ये पुशच्या एक्झॅक्ट उलट. एक्झॅक्ट उलट म्हणजे कसं? पुशला काय व्हॉट वी डू इन पुश? डिक्रिमेंट स्टॅक पॉइंटर बाय 1 and store higher byte. Then again decrement stack pointer by 1 and store lower byte. So decrement and store is the process for push. So for pop, what would the procedure? Listen very carefully and try to have its exact reverse. Decrement stack pointer by 1 and store higher byte. Decrement stack pointer by 1 and store lower byte. Exact reverse. What? Load. Right? So decrement and store higher byte, decrement and store lower byte. Reverse sequence, load lower byte and increment stack pointer by 1 and again load higher byte and increment stack pointer by 1. Is it clear? So for pop instruction the stack pointer value is used as a, so pop instruction किती बाईटचे आहे? 1 byte. C1 D1 E1 F1 pop B pop D pop H pop PSW. So 1 byte instruction, it intends to bring 2 bytes from external memory into a register pair. So how many addition cycles would be needed? 2. In the first cycle of code fetch, in the next cycle stack pointer outputs are coming on address lines, memory read takes place and the data goes to lower byte of the given register pair in the instruction, and then stack pointer is incremented. It is used for as address. The data is read and put into higher byte of the given register in the instruction, and again stack pointer is incremented. So one push and one pop restore the stack pointer. For push, decrement and store higher byte, decrement and store lower byte, load lower byte and increment, load higher byte and increment. So stack pointer becomes same at the end of the one push and one pop. So we start writing down. So what are the opcode sequence? Machines that is value sequence in the memory. 3-1 at 1, 0-0 at 2, 8-0 at 3, 0-1 at 4, 44 at 5, 55 at 6, made a mistake, at 6, C5 at 7, B1, right? LXI H, sorry, LXI SP, LXI B, push B, pop D, right? So we now write down the machine cycle sequence. So how the machine cycle sequence will look like? So type address and data. So first opcode fetch, program counter giving address just now 0000, data 31 going to instruction register. Type opcode fetch, we write less space so that we complete all. Opcode fetch, program counter giving 0000, data 31, 31 going to IR. 31 is the opcode for which instruction? LXI SP. How many byte? 3 byte. So next would be read, but to be specific, instruction read. This is our understanding. Program counter gets incremented. Program counter giving 0001, 00, where this will go? Where this will go? SPL, right? I hope that now at least everybody is clear with this notion. Then instruction read, program counter giving 0002, 80, it is going to stack pointer higher. Now for fetch, program counter giving 0003, 01 going to IR. Instruction read, program counter giving 0004, 44 going to C. Instruction read, program counter giving 0005, 55 going to B. Now fetch, program counter giving 0006, C5 going to IR. So push is 1 byte instruction, but it requires to store. It requires to store something. So what next cycle would be? Anybody? Memory write. How? So it would be a write cycle. Who will supply address? Stack pointer. But there is a need to write something more. What is that? So we write decrement at the top. Lakshya laga meaning. Khali nahi word. Decrement stack, decremented value of stack pointer giving what? What will give? Kiti? What is stack pointer prior to push? 8000. When it is decremented, 7 F F F. एवढं कळलं पाहिजे. नाही तर 7999 सांगू नका. आणि पुन्हा कळत असतं एवढं तर कायच पाहिजे ऑप्शन नाही आहे. 7 F F F. decremented stack pointer giving 7FFF, and what will be stored? Who will give data? Higher byte of the register pair. What is it? C5. Push B. So B will give 55. Is it right? So decremented value of stack pointer, decrement stack pointer, 7FFF comes on address lines, B which is 55 comes on data lines and a memory write cycle. So what next? Decrement stack pointer again. So write cycle, decrement stack pointer which will now 7F, F, E and C giving 44, right? It's over. So push instruction over, then upward fetch. Fetch. Program counter giving 0007. Your code is D1. It will go to pop D. The instruction is pop D. So what will happen now? Anybody? Huh? Other read, right? It will be memory read cycle, but not using program counter. So we have it as other read. Who will give address? Who will give address? Stack pointer will give address, not incremented, only stack pointer right now. And stack pointer will give address which is 7 F F E and then incremented, right? What is there at 7 FFE? 45 may be there. Why I am using the word maybe? मी का मे बी काय म्हणालो? इज दे मी म्हणत नाहीये. समजा मी आता तुम्हाला सांगितलं, मी आता सांगतोय लिहून घ्या. मी सांगितलं लिहून आणि 2 मिनिटं वाचा म्हणतो. तर मी जे सांगितलं तेच वाचलं याची गॅरंटी काय? आर गेटिंग द थीम. म्हणजे आता ह्याच्यामध्ये मी मुद्दाम हे इंट्रोड्यूस करतोय कारण आपण अगदी काही हे ॲक्च्युली जर बालवाडीतलं सगळं शिकवतो हे, मग त्यातून थोडं पुढे येऊया आपण. आर यू गेटिंग मी? आय एम सेइंग 7 FFE and 44 may come. Why I am using the word may? What? No, it's not there. Immediate pop in. So stack manipulation is not there. Anybody? Example पण दिलंय. मी सांगितलं लिहून घ्या. एक आकडा काय सांगितलं, मोठा आकडा सांगितला आणि त्यामध्ये सांगितलं वाचा. मग मी सांगितलंच असेल का? का नसणं शक्यता काय? व्हाईट मे नॉट बी देअर. काय स्टॅक व्होलाटाईलचा नाही प्रश्न, इथं आहेच ना, लगेचच आहे. लाईट गेले असं काही पॉवर सप्लाय केलेलं नाही किंवा असं काही. उदाहरण मी उत्तर आहे का त्यात माझ्या प्रश्नाचं? The answer to my question is there. I think you got it. What is that? No? I say write down something it's very important. I say write down. My job is over. What is my job? Write down and tell contents. What is microprocessor job? What microprocessor does here? Puts address 7FFE on address lines. Puts 44 on data lines and activates write bar pulse. म्हणजे रायटिंग झालं का? 7FFE ला रीड राईट मेमरी मॅप केली असेल तरच रायटिंग होतं. कदाचित मेमरी मॅप नाही असं असू शकतं, विचार करायचा थोडा, किंवा तिथं रीड ओनली मेमरी असं असू शकतं. So in that case, writing will not take place. Is it right? So when I say write, microprocessor performs a write cycle. That doesn't mean that writing has taken place. मी वर्गात येऊन सांगितलं नो राईट डाऊन म्हणजे तुम्ही लिहिलं असं नाही. मी सांगितलं, मी काहीतरी बोललो, तुम्ही लिहून अपेक्षित होतं ते झालं का झालं नाही. पुन्हा याच्या जागा सेन्सिटिव्ह विद्यार्थी असेल तर अकरा लगेच सांगेल आणि एखाद्या नोट नेम करायला नको, तो असेल तर सांगता येणार नाही. मग तो काय सांगेल, आता लिहिलं नाहीये त्यानं, मग तो काय सांगेल. हा आता फरक आहे. म्हणजे मगाशी ते उदाहरण दिलं, सिमिलॅरिटी सांगितलं, आकडा डिफरन्स आहे. आता लिहिलं नाहीये त्यानं तर तो काय सांगेल, रॅन्डम सांगेल. म्हणजे तो हुशार असेल की बाबा काहीतरी सांगून टाकेल, पण तो काय ऍप्लिकेशन नाही करायचं. तर तिथं त्या पानावर काय असेल, मी लिहा म्हणलंय, यानं लिहिलं आणि कोणतं लिहिलं नाही. मग त्या पानावर काय आहे, हे वहीतल्या पान आणि मेमरी लोक यातला फरक आहे. काय फरक आहे, वहीतल्या पान मध्ये काही नाही असं असू शकतं, ब्लँक. मेमरी कधी ब्लँक असत नाही. म्हणजे इन दिस सायकल व्हॉट मायक्रोसॉफ्ट डुईंग, इट इज पुटिंग 7FFE on address lines and activating read bar. Something will come. If nothing is there, all ones will come. All ones will come. So it will be FF. It will means if no memory is mapped, FF will come. So there is no question of blank data in microprocessor or in digital games, right? So if everything is going smoothly, then 44 will be there, and where it will go now? 44 would say, where 44 will go? Which register? Load lower byte and increment stack pointer by 1. It will go to which? Push B होतं, pop D है, so it will go to register E. Then again other read stack pointer giving 7FFF and again incremented, so stack pointer is restored at 8000 and 55 will go to D. 55 will go to D. Is it right? Is it okay? Push and pop. Push and pop. These are stack read operations. So, what is the advantage of this is that suppose that you want to use the registers for some other purpose. So you want to store all 4 register pairs in the memory. So still you can do by using different operations. Move B to A, STA, but each time you have to take care of storing at next location. Or you can use using move M comma A, move M comma INXH, move M comma B, like that. But the problem would be for storing that you have to use HL pair. So original value of HL pair needs to be stored somewhere else. So without using push instruction, you can still store the all register contains in memory at some block, but for that purpose you have to use HL pair. So you have to store HL pair somewhere first using SHLD. Using SHLD you have to store HL pair first, then you have to initialize HL, then you have to store byte by byte in the memory. Each time you have to increment HL pair manually. Each time you have to increment HL pair manually. By this way you can do. But what push allows you? Push allows you to store it in an automatic process by incrementing or decrementing stack pointer continuously. Means now there is a concept of subroutines. आता हे असं आहे की आधीच सांगितलं, आधी काय सांगायचं मग काय सांगायचा प्रश्न पडतो. आधी सबरूटीन शिकूया आपण आणि मग ह्या पुश ऑपरेशनचा मिनिंग शिकूया. सो व्हॉट इज सबरूटीन? इफ द सेम टास्क आपण मल्टिप्लाय बाय शिफ्ट अँड ॲड मेथड शिकवतो पूर्वी, आता पुन्हा आपण ते घेतलेलं नाही, ते पुढच्या लेक्चर आपण घेऊया पुन्हा एकदा, पण तुम्ही एकदा परत वाचून घ्या. सो some kind of task which is to be carried out is done by group of instructions, and if that task is to be carried out repeatedly, in that case I would write that group of instruction continue each time. म्हणजे एका ठराविक काहीतरी काम आहे, 2 8 बिटच्या नंबरचं मल्टिप्लिकेशन करणे, ते आपण वेळ वाचावा म्हणून शिफ्ट अँड ॲड मेथडने करू शकतो. मग ते मल्टिप्लिकेशन सारखं करायला लागत असेल, सारखं बऱ्याच वेळा काही नंबर्स येत आहेत त्याचा मला मल्टिप्लाय करायचं, एवढंच पर्पज आहे. तर काय करायला लागेल मला, तो एक 10 इन्स्ट्रक्शन्स आहेत, ते 10 इन्स्ट्रक्शन सारख्या लिहायला लागतील. म्हणजे आता हे मल्टिप्लाय रूटीन काय करत आहे, ॲक्युम्युलेटर मध्ये एक नंबर दिलेला आहे आणि बी मध्ये ई मध्ये नंबर एक घेतो आपण. सो जे आपण शिफ्ट अँड ॲड वापरून मल्टिप्लिकेशनचं सबरूटीन दिलंय, what a program does, if we provide one number in E and other number in accumulator, then it performs the multiplication operation and returns the value in HL pair. म्हणजे A आणि E मध्ये नंबर्स दिले तर तो HL pair मध्ये मला रिझल्ट देतो. मग आता याच्यामध्ये मी काय वापरतोय, A आणि E मध्ये नंबर देतो. मग ए आणि ई वापरू लागतात. मग आणखी फास्ट काय करू शकतो मी, HL मध्ये नंबर द्यायचे. म्हणजे आय कॅन कॉल द सबरूटीन बाय सप्लाइंग 1 8-bit नंबर इन H, अदर 8-bit नंबर इन L, and what it will do, it will perform calculations and give the result back in HL pair. लक्षात आलं का? H आणि L मध्येच नंबर देणार, प्रोग्रामच्या आतमध्ये तो पुन्हा ए मध्ये घेईल, ई मध्ये घेईल, डी 0 करेल, HL पुन्हा 0. आपला शिफ्ट अँड ॲडचा प्रोग्राम आठवतोय का? शिफ्ट अँड ॲडचा प्रोग्राम आठवतोय का नाही? तर त्यामध्ये आपण काय करत होतो, ए आणि ई मध्ये रजिस्टर घेत होतो, व्हॅल्यू घेत होतो आणि HL मध्ये रिझल्ट मिळत होता. सो नाव व्हॉट वी डू, वी गिव्ह नंबर, मीन्स we supply numbers in H and L, the program will compute the multiplication and the result would be back in H and L. Is it right? So a group of instructions required initializing accumulator with first number, initializing E register with second number, making D 00, making HL 00, and then rotating all these things. All this, a block of instructions when executed, what it does is that whatever are the values of H and L at the beginning of this block, when the block of instruction is executed, at the end of the program, this H and L, if this original L contains N1, original H contains N2, then H and L together contain N1 N2, right? Is it clear? So this is a block of say 10, 15, 20 instructions which when written in the given order computes multiplication of the numbers given in H and L, and the result is stored back in H and L. So in this entire program it uses various other registers for calculation purposes. Now if you want this to be repeatedly used, then each time you have to repeat. So that would be a very non-efficient way of programming. Your memory space will be utilized, number one, and if it may be for few thousand times. So there will be a problem of memory size also, because even though it is 64K, we find it more, but if it trades for many times, then there will be a problem of using the manual memory also, and we have to write each time. That is also cumbersome process, and those days writing was not so easy. Actual feeding or the manual feeding was there sometimes because that time computers were not there, so manually feeding was also required many times. So in general, this is something to be avoided. Therefore, a concept has come of, so this, so if I start my program from 0000 onwards, then at some time I would require to write this. Now after some time again I would require to write the same instructions. So instead of writing it many times, what I do is I write at some fixed location, say 9000. At 9000 I write this stream of instructions, right, at 9000. And when my up to this is over, and what I am expected, whenever I want to refer this, I should go there. So in my main program, suppose that I want now this, so I should branch there. So that I can do using which instruction? Jump 9000. That I can do using which instruction? Jump 9000. And whenever this is completed, so if I am at 0009, I write jump 9000. So 9 A and B. So what is, where the next instruction would be? 009 ABC, right? So I should come back at 000C. So this program starts at fixed address, so I can go there by writing this. But how I will know to come back here? Because this will be different, because I want to use that group many a times. So writing jump and giving address okay, but this should be something which should be again a branch instruction, but it should come branch at a variable address. So when the concept of subroutine, I will now explain slow speed English bulletin. Some specific task which is requiring a bunch of instructions, and if I require that task to be executed a number of times, in that case I would write that bunch of instructions all the times whenever I require. That makes the program too big and non-manageable. Rather than that, a concept of writing those instructions only once somewhere else. Only once somewhere else. I will give another example. Suppose that a master-servant case. Can master do calculations? Yes. But he is bored. He doesn't want to do. So he is doing something, and a servant is aside. Calculators were not there, say. So what master tells? Oh yes, now you do 53 into 54. He tells the servant. The servant does it, gives value, then he takes that value and proceeds again. Right? So assign the task to servant each time. So each time again, yes, now 93 into 97. He calculates, gives that. So what is done is that bunch of instructions is written at some fixed address in 9000. So in that case, from whenever that is to be referred, I can go there by jump 9000. But the problem is that how I can come back. How I can come back. I can't come back because 000C. I can't write jump 000C there. If I write there, then it would be only coming there. It should be means the last so the last magic instruction in this should be branched at a variable address. it should be branch at a variable address. Branch at variable address. Is it right? Now, what designers have thought, we already discussed stack operations. So, if this is to be branch at variable address, then it should be a single byte instruction. It should take address from somewhere. It should take address from somewhere and then branch. So this magic instruction is pop PC. Listen now very carefully. The magic instruction is pop program counter. त्याचं नाव वेगळं आहे, मुद्दाम तुम्ही पॉप पीसी. सो दिस इज पॉप पीसी. द मॅजिक इन्स्ट्रक्शन. फक्त बाहेर कुठे विचार सांगू नका, नाहीतर काहीतरी असलं काहीतरी शिकवतात काय म्हणतील. सो जे वर्गात मी सांगतो त्यातला काही पार्ट क्लासिफाईड आहे. क्लासिफाईड म्हणजे आपल्याला तो लपवायचा नाही आहे, परंतु तो व्यवस्थित प्रकारे त्यानं ते घड्याळ बघितलं अजून किती वेळ आहे, म्हणजे त्याला काळजी लागली की हे आज हे पूर्ण होईल का नाही. तर तुम्हाला जोपर्यंत सांगण्या इतकी ॲबिलिटी आहे असं वाटत तो पण सांगू नका. सो द मॅजिक इंस्ट्रक्शन इज पॉप पीसी. सो दिस इज सब रूटीन and the magic instruction is pop PC. So what it will do? It will branch. So pop program counter. What it will do? Program count is otherwise manually, automatically incremented by the microprocessor itself. So pop PC will do what? And the core of pop PC is C9. Core of pop PC is C9. So what it will do? Read stack, use stack pointer as an address, read that memory location, put that value into program counter lower byte, increment stack pointer by 1, read the memory location again using stack pointer as an address, put that value in program counter higher byte, increment stack pointer by 1, and then use the next is opcode page, for which program counter will be used. What program counter? Means this pop PC has changed the old program counter. So if pop PC is to come back at 000C, will it come back? How? But that 000C should be pushed first. If I want it to come back here, so 000C should be pushed first. So then we should have separate instruction. We should have a separate instruction, and that instruction is call instruction. So the instruction is call, and now I hope that I tell and expect you to write call 9000. Call 9000 is a combination of one hypothetical instruction call is a combination of one hypothetical instruction push PC and one real instruction jump at same address. Call is how many byte instruction? 3 byte instruction, because call address 60. Call address 60. Right? So now with this I write the set of instructions, and you should be able to write down the machine cycle sequence. LXISP 8000 0003 Alexa H 5544 0006 COM 9000. At 9000, at 0000 what we have? At 0000 we have 31, at 1 we have 00, at 2 we have 80, at 3 we have 21, at 4 we have 44, at 5 we have 55, at 6 we have call of course CD, at 7 we have 00, at 8 we have 90, at 0009. Next, let us say that some other instruction, new instruction, and at 9000 we have entire sequence of multiplication of H and L by a long program. From 9000 the program ends at say 9010, and it is POP PC, or POP PC is hypothetical, its actual name is return. Return, RET, it is as good as POP PC. So from 9000 onwards, whatever it may be, and at 9010 we have C9 as the opcode of return. We have C9 as the opcode for return. So with this now, we start the so type address data. I think up to 0 to 5 there is no need to write. Is it required? 0, 0, 0. Anyway, we will fast. Fetch program counter giving 0, 0, 0, 0. Data is 31, that goes to IR. Instruction read program counter, instruction read program counter, fetch program. I think now each time this you may not require, means you should know that when it is instruction read, or each time program counter plus 0, 0, 0, 1, 0, 0, 0, 2, 0, 0, 0, 3, 0, 0, 0, 4, 0, 0, 0, 5. When IR, when program count, when F, it is always IR, it is Alexa H, 21 goes to IR, 0, 0 goes to where? SPL, 80 goes to SPH, 44 goes to L, 55 goes to H. Now most important, fetch program counter giving 0006, opcode is call, CD, going to IR. Call is how many byte instruction? 3 byte. So what is next? What next 2 bytes are meant for? Next 2 bytes are meant for. Next 2 bytes are meant to be the new address where it is supposed to branch. New address where it is supposed to branch by storing current PC. So at least next 2 bytes. So instruction read program counter giving 0007, 00 will come. Instruction read program counter giving 0008, program will implemented 90. Where 00 will go? Where 90 will go? Call 9000. What is 9000? 9000 is the branch address where the program is supposed to go. So 9000 is the value which will be the new value of the program counter. So it is required afterwards. Right now it is being read. So it should be stored in Z and W. So Z and W. So what is the difference between jump? If it is jump, if it was C3, what should have happened? Here itself we have written that program counter getting assigned to. If this is jump instruction, then here only we have written into bracket program counter getting assigned to WZ. So next instruction should have been opcode fetch from 9000. If this was a jump instruction, then in jump is a 3-byte instruction. In the first machine cycle opcode fetch, in the second machine cycle reading a lower byte which would be going to serve as lower byte of the program counter later on. In the third machine cycle reading higher byte which would be going to serve as a higher byte of the program counter later on. So since it is later on, it should be stored in these two cycles. So in the second machine cycle, instruction read, program counter giving address, lower byte of the branch address goes to Z. In next, program counter gives address, higher byte of the branch address goes to W, and after that into bracket here itself I would have written that program counter getting assigned to WZ. That I should have written here itself if it was jump instruction, but now it is not jump, so it is call. So call is something plus jump. What is that something? Push, PC and jump. So call instruction is fetched. Call instruction is fetched in 3 bytes. Now what is to be done? It is to be executed. What it is? Push, PC and jump. So what should happen now? So let everybody think and tell me what the next 2 cycles would be. So by uttering next 2 cycles I have given you a hint. Which cycle? Right cycle. So next 2 would be right cycles. Why? Because it is push PC. Right. Right. Who will give address? No. One small correction. Stack point will give address is correct, but decremented value of stack point will give address. So first decrement stack pointer by 1. So what it would be? Stack point would be 7FFF. Who will give data? Who will give data? What is to be stored? Call 9000 is push PC and jump 9000. So program counter higher byte will give data. So program counter higher byte, what it would be? PCH किती आता? आता program mode किती आहे? What is program mode right now? 0009. इथं 8 झालाय.